Swayam Prabha. Digital India. Educated India.
So what you have is that you remove an electron from the core level, which you are doing here. Same thing. Now, once this goes away, you have a core hole. The atom is now unstable in an excited state. So it has to relax. The way to relax is there are two ways of relaxing. One is this electron just above can jump here. So if it is coming from here to here, that energy has to be released. Right? That energy has to be released. So that energy is now picked up by this electron and it comes out as OJ. Okay? But this OJ intensity is very low. Very low. Okay? Alright? So that is how you can actually figure out.
In that process, are there two electrons being released? Like one the OJ electron and then the other one takes a core. So two electrons are released.
Many electrons will come. Not only 1s, 2s, p, d, all electrons will come out from the sample. Because you don't have one atom, you have I've got a number of atoms.
No, I'm asking for a single atom. Will there be two electrons coming out?
Single atom, I think it's only one process will take. Otherwise, atom will be unstable.
You said the electron from the core shell goes out, and to satisfy the energy gap, the electron from the other shells come in and fit the instability. So there's one electron which picks up the energy and gets released as OJ electron. So other two electrons getting released from the same atom.
From here. Yeah, two electrons are released here. Two electrons are released. But remember, this process is very fast. It's about 10 to the minus 15 seconds. Very fast. And it gets neutralized because this is a conducting sample. Immediately it gets neutralized. The process takes place, immediately gets neutralized. Otherwise, the sample will become a charge. You will have a charge on that. So your spectrum will get distorted. So it has to be a conducting sample, or otherwise you have to find a way to neutralize the surface charge that is developed on the surface.
So you said that once an electron moves out due to spectroscopy, it knows where it comes from. So how does it go back to its main?
It will not go back. It will go into the analyzer and then where you catch it and then measure the kinetic energy and then see how many of the same kinetic energy electrons are coming out, you catch them. Right? So once you do that, then what you have is so you start getting peaks. They count how many electrons are coming out for that particular kinetic energy. Right? You have so many atoms, no? So if the intensity is X-ray intensity is very high, it can actually ionize many atoms, and then electrons will come out at that particular kinetic energy. So many will come out. So you can count how many electrons are coming at that particular kinetic energy. And these electrons will go through the analyzer and it will get into the detector.
So the released electrons, do they interact with the external environment in some way?
They will. That is the next step I am going to come. You are not supposed to, you should not allow them to interact with the environment, the gas molecules. So the whole experiment should be done in vacuum.
Do they react differently, like the Auger electron and the electron from the core, do they react differently with the environment? Or all these?
No, there is no environment there. See, entire experiment is done in vacuum. Vacuum is of the order of 10 to the power minus torr. 10 to the power minus torr. 1 torr is 1 millimeter Hg. So atmosphere is 760 torr. So you have to reduce the pressure of the order of 10 to the power minus 9 torr. That means 10 to the power minus 9 millimeters Hg, mmHg. So at that pressure, or we can now you can call it a vacuum, the mean free path of these electrons is going to be pretty large. So they will not collide with anything on the way. If it is a if you do it at high pressure, the electron will not reach the will not go through the analyzer and then it will not reach the detector. You have to have the mean free path of that should be sufficient enough so that it will go from the point way of ejection to the point of detection. That's the reason this experiment is usually done in vacuum. In vacuum.
What do we mean by the memory of an electron?
Memory of the electron, yeah, right. So you are coming from which school?
TI.
Huh?
TI school.
You are coming from which school? See, that is the memory. She is coming from that school, you are coming from that school. Electron also, electron is coming from sodium atom, electron may be coming from copper atom. Right? So when it comes out of that particular, suppose say copper, scandium, titanium, vanadium, chromium, manganese, iron, cobalt, zinc, you have in the first row transition metals. So in each of these atoms, if you see a d electron is d electron of course, but then in each atom the d electron will have different energy. Right? So you remove an electron from titanium or vanadium or chromium, same d electron, but it will have a different binding energy, different kinetic energy also. So you measure that, right? So then that will tell you that from that you can figure out which element it is coming from.
So is that because of the nuclear interaction?
Yeah, absolutely. That value changes, no? Right? That value is different. So your nuclear charge is increasing or decreasing depending on where you are going. So if the nuclear charge is high, the binding energy will be high, kinetic energy will be less. So that is a characteristic of that particular element. Okay, right? So that is how it is.
Sir, this memory that the electron has, right? In the valence electron, it experiences lesser nuclear attraction compared to the core electron. When it reacts with some other element or something, does it like slowly lose that memory and becomes a part of the compound itself, or does it retain the memory?
I use the memory. I thought because if the core electrons are removed, these electrons are very localized electrons, whereas valence electrons are not localized; they are delocalized in the band, right? So the localized electrons, if you analyze that, you'll be able to figure out which element it is coming from. Whereas delocalized electrons in D bands, they will not carry much of information. But still, no, you can actually do it in a different way, but they don't carry much information about the element. Okay,
So
I hope I.
become a part of the compound as a whole. So does the memory play any role in the chemical reactions, or it's only used?
Of course, the valence electrons are very important.
No, the memory that the electron carries from where it comes from.
Okay, all right. So suppose say you take an atom. It is oxidation state is 0. I'm going to come back to that point. You are asking the questions ahead of what I am teaching. You have an atom with positive charge. Initially 0, atom valence, the charge is 0, then +1, +2, +3. So I remove an electron from one of the orbitals, one of the energy levels. The 0, +1, +2, +3 will not have the same value because of this. The charge is increasing, so the binding energy will increase because the nuclear influence is more on that, right? So if this atom is present in a compound with whatever oxidation state, then definitely it will get influenced. Then that is what is called a chemical shift. I will come to that point little later. Right? Okay, I will come to that point quickly. All right. So I think I will skip this. Yeah. Now let's look at this particular slide. Photoabsorption is very fast, 10 to the power minus 16 seconds. Now you see, let us look at these points here. No photo emission for HNU is less than work function. Is that a correct statement?
or otherwise it becomes negative.
Do you agree with that statement?
Yes, sir.
Right? That is simply photoelectric explanation of that. Now second one, no photo emission from levels with binding energy plus phi greater than h nu. Look at this one here. This expression. Right? Now, kinetic energy of photoelectron increases as binding energy decreases. Is that a correct statement?
Yes.
Again the same expression. All of you follow?
Yes.
Now the next statement is it requires monochromatic incident photon beam. Photo emission experiment requires requires monochromatic incident photon, because the h nu has to be fixed. H nu cannot be h nu and h nu, you cannot have that, it has to be precisely known. That is also correct. A range of kinetic energies can be produced if the valence band is broad. Valence band is broad, it's not well defined, it's a broad one, So you will have electrons with different various kinetic energies. So it's a band, so the electrons also come out from any of these places, so it will become very broad peak. Okay, that's what it means. Therefore, kinetic energies and binding energies can be used to fingerprint the element. That's what I was talking about, memory effect. I'm just using that word so that you understand it. Right? It's a fingerprint of a particular element. Right? That's right. So binding energy is the energy of the electron present in a particular level. Suppose a 1s electron sitting in a 1s, it is a particular energy. For example, hydrogen 1s electron. What is the energy? Binding the energy of the 1s orbital in hydrogen atom. That is binding energy. Phi comes into picture when there is a metallic surface where you remove the electron from a bunch of large pool of atoms. You remove the electron, but it creates positive charge there. So the electron will not be free immediately, because it has a memory effect, and it has a positive charge which is pulling it back. So it has to overcome that. So the energy required for that is nothing but the work function. Okay, all right. Now let's look at this. Now you understand many things. Now you look at this. We look at this one. I can even use this also, right? Yeah. Now here, if you see, binding energy represents the strength of interaction between electron and nuclear charge. Obviously, right? Yes or no? N, L, M, S are basically your quantum numbers. Electron is present with a particular quantum number, will have a particular binding energy. That electron will interact with the nucleus and it will have a particular energy. Interaction energy, right? You call it as. Okay. Now, by looking at this, in gases, binding energy is equal to ionization potential, because in gas the molecules are isolated, separate, not like a solid or a liquid where they interact. It's individual molecules. So you can ionize this, for example, when you take a diatomic molecule, pi electrons are there, you can remove pi electron. That is your ionization energy of the pi electron sitting in a molecule. Okay. Now look at the second one. The binding energy of 1s electron is greater than binding energy of 2s electron, is greater than binding energy of 2p electron, 3s electron, and so on. Do you agree with that? 1s electron is very close to the nucleus compared to 2s electron, compared to 3s electron. So 1s electron we have higher binding energy, right? And so on and so forth here. So it follows the electronic structure of atom. You recall that electronic structure they must have taught you, right? Electronic structure, right? So the electronic structure, what you are learning is basically the proof of that one is nothing but photoelectron spectroscopy. Photoelectron spectroscopy can give you the proof for that, right? Now come to this one, next one. Binding energy, N1s electron and magnesium 1s electron, this is sodium, magnesium, aluminum and so on and so forth. Now it is less, 1s is less than 1s of aluminum is so on and so forth. All are 1s electrons, but this has lower energy compared to this and this has lower energy compared to this. Is that correct? Do we understand that? So why is it so?
Sodium has one charge.
Nuclear charge is increasing. Nuclear charge is increasing. So all these things, if they are true, then your photoelectron spectroscopy should show that in the spectrum, right? If all these ideas are correct, right, then our photoelectron spectrum should show that, should give evidence to that, experimental evidence, right? So that's the story. Now you see, binding energy orbital is not affected by isotopes. Do we agree with that? Because isotopes, all that is changing is you may have extra neutron, right? But that is not a charged particle, right? So binding energy is not expected to be different, right? So these are some of the points which we keep in mind, and then we move on. All right. I skip all this. Okay, I'll just show you this example. For example, as I was talking about, you have this. These are all core electrons. See, these are all localized electrons. They have sharp energy. They have specific energy here. But as you keep going up, this becomes like a band. Now, suppose say now this one, as you keep increasing, there are all energy levels. All these energy levels are filled with electrons. Now, if you keep going, so somewhere here you have Fermi level. Fermi level is the highest energy level where the electrons are occupied. Beyond that, there are no electrons because all the electrons are occupied. All the energy levels are occupied. Whatever electrons are available in the atoms, they occupy up to that level. Beyond that, you may have energy levels, but there are no electrons here. Okay. Now, what we do? This is called Fermi level. That is referred as EF. Somewhere here, EF. Fermi level, Fermi energy. You will come to know a little later when you go to higher classes what is Fermi energy. Right now, you remember that it is a energy at this point. Okay, that is the highest energy level the electrons occupy. Now, you remove an electron from here and it goes out, and that is the work function. That is the work function that is required to remove electron from the influence of the surface or the atom where it is ionized. So people call this as vacuum level. This is imaginary one. Basically, you are removing the electrons far away so that it doesn't come under the influence of the surface or the atom where it is ionized. So, right? So that is the energy that is required, work function. So remember these things. What are we introducing here? Lowest energy state. Electrons are localized in here, and then as you go up, you see these are binding energy levels, different levels with binding energies, and this is the Fermi level. From here to here, it is called work function, right? So this is something which you keep in mind. When we go to the spectrum, we will use this information. Okay, so now since we said the atom is excited now, you are removing the electron here, photoelectron, and then the atom is excited here. This atom can actually relax in two ways. One is X-ray can come out, other one the Auger electron. This already I have explained to you, Auger electron. But this X-ray which is coming out is used to remove this electron. That's why the Auger electron is coming out. Suppose if it is not used, then it will come out as X-ray photon. So that is one way of decay. So you can have a X-ray coming out, or the same energy can be used to remove a Auger electron. These are the two ways of relaxation, relaxing the excited electron the atom. Right? So, if you have atomic number smaller, this less than 15 atomic number Z, you see more of X-ray coming out, no X-ray is coming out. But if it is beyond this, X-ray yield is high, that means X-ray is coming out more. And then for the elements like oxygen, carbon, nitrogen, the original electron emission is much higher. That's why it is very easy to detect them using original emission. Okay. Okay, don't worry about it. But the point is that original emission is more if with the atomic numbers less than 15, and X-ray emission starts increasing as you go to higher atomic number, and at the same time original intensity comes down. This is an experimental graph. This is experimentally drawn graph. Okay, all right. Don't worry much about it. Okay, I'll just show you this slide where I had shown you earlier. These are electrons. This is the band which we were talking about, valence band, the valence electrons. Okay. Now suppose say, and this is the phi. This is a vacuum level. This is phi. That is EF. Correct. See, electrons are there filled up to this point. Up to this point. Beyond that, no more electrons are available. Suppose say 1 mole of sodium atoms, if you take, how many electrons are there? 1 electrons? 1 mole. It can't be more than that. Right? So number of electrons are limited. So they keep adding here. So it will come to this point, that is the highest they can come. So when you record this, when you actually do the photoemission experiment here, all that is you are seeing here will be mapped here. This is the spectrum. You see, these electrons when they come out, you have a peak. These electrons when they come out, you have 2 peaks, and this will give you a broad peak like that. So you are exactly mapping the electronic structure of the metal. Okay, all right. Now this EF is taken as 0. That is a reference point to. It is something like, you wanted to measure the height of the tree. You don't go below the ground, right? Ground is the reference point, and then from there you measure the height. Similarly, you can take it as 0. That is a reference. Fermi level is a reference level. From there you start measuring. These are the binding energies. As you go down and down, you are actually approaching closer and closer to nucleus. That's why the binding energy keeps on increasing. So you have 5d electrons. Let us say this is one of the transition metal. Let's say copper or so 5d, 5p, 5p. You see all these orbitals, all these energy levels, the d orbitals, p orbitals. So you start probing them. Right? Okay. So this is how. This is the instrumentation. You have electron energy analyzer. See, basically this is what is important for us. This X-ray tube, that is your sample. The X-ray is coming here, and then it ionizes the photoelectrons. These electrons they pass through the electron energy analyzer. That analyzer will measure the kinetic energy precisely. And then you have kinetic energy here. Right? And how many electrons are actually coming out from that? From that is the measured as counts. So you get a spectrum like this. Okay, all right. Of course, you have then the ultra high vacuum is required, as I mentioned, 10 to the minus 9 torr, because electron should not lose its kinetic energy. That's the reason why you have to have a vacuum, so that the electron passes through this and then comes out here. There will be a detector here. Okay, all right. I think remaining things, don't worry, there are a lot of electronics and all other things are there, don't worry about that. This is the spectrometer. Okay, this spectrometer is something which, it was bought somewhere in 1975, 77, one of the oldest spectrometers in India. It was bought from, there is a company in UK, so they purchased it. This is the machine. It looks very complicated, right? Huh? It's not very complicated. If you go to that lab, in just 1 hour you will learn it. You guys are very sharp. But for me, it took several months. I was even very scared to go near to that. But now you will not be scared because you are handling these sophisticated cell phones. Entire world is there in that. You will pick up in just 1 hour, you will start operating. Those days we don't have cell phones. Okay. Alright, so now here this is a modern spectrometer. It just installed in 2022 in ARCI, just other side. There is one machine came just now to IIT Madras, is being installed in one of those new buildings. This is a new, this is the current one, this is the old one. But this is gold is gold. You can do a lot of interesting things here. And this one is very limited. You can analyze, but if you want to design an experiment, this will not be able to do that. This is a machine which was built in National Chemical Laboratory, Pune, to do this experiment. You can see now here, you can do a lot of things. You can actually design, I want to do this experiment in this particular, using under these conditions, etc., etc. You can define that. So this is the experimental machine which was built in National Chemical Laboratory, that is published in Journal of Physical Chemistry 2013. That costs about 4 crores. Now it is about 6-7 crores. Okay, all right. Okay. We are saying that we are using only these two X-ray photons. There is something called synchrotron radiation. So here what happens is, I'll just use this one. There is a ring here. The ring is a kind of a tube. That ring with the diameter can be a few meters to kilometers. Meters probably may not be kilometers, but the huge ring. So you inject electrons into this. You inject electrons into that, and these electrons, you keep on accelerating them. They will move around in the ring. But then in a charged particle which is actually going in a linear fashion, it will not give out any radiation. But if you try to bend it, electromagnetic theory, if you recall, you try to bend it, it gives out radiation. So now that is a ring. Electron is going around, and there are magnets here. Okay. And these magnets, try to bend the beam which is actually going around with a particular energy. The energy can be in giga electron volts. So when you bend it, it gives very intense light. So these are all intense lights coming out. All these lines, these lines. So that can be X-ray. It can be X-ray photon. It can be IR photon, or variety of continuous energy. Spectrum will be there. So what you can do is, if you instead of 1486.6 electron volts, I wanted to choose 1000 electron volts photon and then do the experiment, photoemission experiment. You can do that. And then the beam intensity is very, very high. It's like a laser. Very intense beam comes out. So your spectral features are going to be, intensity is going to be very high. Okay. So this is not a laboratory one. This is actually specifically in a synchrotron radiation center. There is one we have in Indore. In Indore, there is one synchrotron radiation center where there is a dedicated beam line for doing photoemission experiments. Okay, all right. Yeah. So this is another way of doing it. Of course, students from IIT Madras they go to Indore and do some of these experiments there. Okay. But in the laboratory, you have only this. This is something which is fixed in the laboratory. Okay, so this is how it looks like. That is X-ray, and that is the electrons are coming out. The yellow one, it goes through this analyzer, and all the electrons which have a particular, because there is a voltage applied between this and this. This is a constant ring like this, hemispherical. So electron enters into it and it comes out like that. So you have a positive charge and negative charge, so that the electron takes a particular path and then comes out and then goes to the detector. This is detector, right? So this energy, this voltage, you can keep on changing. That means, you actually are allowing the electrons with the different kinetic energies passing through the analyzer. So if you know the voltage, that is related to the kinetic energy. That is related to kinetic energy, right? So you are measuring the kinetic energy, and then you are counting how many electrons are coming out here. All other electrons will disappear. They can go and hit this surface or this surface. They will disappear. That is how you isolate electrons of particular kinetic energy, and then measure their kinetic energy, and then count them. How many of them have the same kinetic energy? That is the spectrum. That's how you get your spectrum, right? So you need vacuum. As I said, there are several ways of producing vacuum: diffusion pumps, mercury diffusion pumps, turbo Markov pumps, so on. These are all basically some technical things. These are the pumps which are used to create low pressure or a high vacuum. Low pressure or high vacuum. Okay. I don't have I don't have it now. So that vacuum is something related to kinetic theory of gases you have studied. So from there one can actually figure out, saying that you need number of atoms hitting the surface is equal to this one. So if P is equal to very small, it comes out to be Ns equal to 10 power 6 into P monolayer. So if P is 10 power minus 6, then it takes 1 second to contaminate the surface. That is the reason why you need to have minus 9, not minus 6 itself is not sufficient, because you will not be able to finish your experiment in 1 second. You go to 10 minus 9 minus 10, then the surface can be clean, can be kept clean for about an hour or so, during which you can finish your experiment. Okay, this comes from the kinetic theory of gases. Okay. So this is the ring. I just told you, this is called Indus 2 in Indore. I think I have it here. Raja Ramana Center for Advanced Technology, Indore. If you want, you can just go have a look at it. It's a very nice, beautiful website, and you will see a lot of interesting things there. So you just say Raja Ramana Center for Advanced Technology, Indore. You get that website. All of you go and spend some time. You will be able to see what it is. Government of India has spent a lot of money to create that center for us, for all the students or faculty who are working in India. Okay. All right. We continue, or is it too much, or are you enjoying it, or is it too much? Or you want to take a break or something? Or we continue? I have no problem. I will continue for 1 hour, another 1-2 hours. Sure, definitely. I can go until 5-6 o'clock if they are ready to listen. Sure. Thank you.